Hello everyone, welcome to the Mathematics MI channel. In this video, we are going to solve this interesting integral. Integral from minus infinity to infinity sine of x over x minus I dx. Okay, how to begin? Well, here we have boundaries from minus infinity to infinity. So as a first step, I am going to break the limit like minus infinity to 0 sine of x over x minus I dx plus then we know 0 to infinity sine of x over x minus I dx. Okay, now for this integral, first integral, I'm going to make a substitution. X is equal to minus u, then if we differentiate, dx is equal to minus du. Now we can plug in. So here now we should change the boundaries. We know when x approaches to minus infinity, u also approaches to minus, so positive, so infinity. When x approaches to 0, we know u also approaches to 0. Then here sine of x we know minus u, sine of minus u we know minus sine of u over x, again minus u minus I dx we know minus du plus here 0 to infinity sine of x over x minus I dx. Okay, then here we can change the boundary like infinity to 0 we can change as 0 to infinity. When we change the boundaries, this minus sign get cancelled, and here we have sine of u. Now in this integral we know variable u, but we know definite integral independent of the variable. So instead of u, I am going to plug in x. So here sine of x over here minus sign, here minus minus. So if we take minus sign as a common factor, we have minus over minus, we know plus. So here we have x plus I dx plus integral from 0 to infinity sine of x over x minus I dx. Well, now we have same boundary 0 to infinity, 0 to infinity. So 0 to infinity. Now I am going to take the common denominator. We know we have x plus I times x minus I. Here in the numerator we know sine of x is a common factor. So here x minus I plus x plus I dx. Okay, we know minus I plus I get cancelled. So we have integral from 0 to infinity x plus x, we know 2 times x sine of x over, now here we know difference of 2 is squared, so x square minus I square dx. Okay, now we know 2 is a constant, so we can take outside of the integral sign, integral from 0 to infinity x times sine of x over here x square minus I square we know minus 1, so x square plus 1 dx. Okay, how to solve this integral? Integral from 0 to infinity x times sine of x over x square plus 1. So we have several methods. In the previous video last week I solved this integral by using Laplace transform. So if you like to watch that video, please check the description. I will add the link and also make a card. So we know here the answer of this integral we have pi over 2 times e. So if not you can evaluate this integral by using this integral, very famous integral. We evaluated this integral by real method. If not, you can evaluate this integral by using complex analysis. Here x square plus a square dx is equal to pi over 2 times a e to the minus ab. I will add the link of the solution of this integral in the description. So now if we differentiate both sides with respect to b, we know the derivative of cosine, we know minus sine. So minus integral from 0 to infinity here coefficient of b we know x, so we have x times sine of bx over a square plus x square dx is equal to here pi over 2 times a derivative of e to the function, so e to the minus ab times minus a. So here minus a, now we know a get cancelled, this minus sign and this minus sign get cancelled. So we have integral from 0 to infinity x times sine of bx over a square plus x square dx is equal to here pi over 2 times e to the minus ab. Now let's apply when a is equal 1 and b is equal 1. We know we have integral from 0 to infinity x times sine of x over 1 plus x square dx. This is our integral, and we know this is equal to pi over 2, here e to the minus 1 we know 2 times e. So we have same answer. If not, again you can evaluate this integral by using complex analysis. So here now however we have 2 times pi over 2 times e, so 2 get cancelled and we have pi over e. Okay, this is the answer for this interesting integral. If you like this type of videos, please subscribe this channel. Thank you for watching.